All right, let's get right into it. Today, we're doing a deep dive into the absolute bedrock of containerization, the Dockerfile. We're going to go way beyond the basics to really master the instructions you need to build secure, efficient, and truly production-ready images. And you know, this quote really nails the core idea for today. A Dockerfile? It isn't just some script you run. Think of it as a formal contract. It codifies your application's entire world, its environment, its security posture, and how it behaves at runtime. Getting that contract right is, well, it's everything. So here's our game plan. We'll kick things off with that big idea, the Dockerfile as a contract. Then we're going to hit the most critical instructions one by one, choosing a base with from, executing commands with run, getting our data inside with copy and add, and finally setting up the environment. Let's do it. See, when you're writing a Dockerfile, you're not just automating a setup process. You are making explicit, serious architectural decisions. These decisions define how your app is going to behave everywhere, from your local machine all the way up to a massive cloud deployment. This file is literally the blueprint for creating containers that are predictable and disposable, what we call immutable and ephemeral. Mastering these instructions is the absolute key to building systems you can actually rely on in production. Okay, let's get our hands dirty, starting with the from instruction. This single line right at the top of your file is probably the most important architectural choice you're going to make. It's like the genetic makeup of your entire container, and it sets the stage for everything that comes after. So, when you choose a base image, you're making a fundamental trade-off. On one end of the spectrum, you've got full distributions like Debian. They're huge, they're jam-packed with tools, and that's great for convenience. But on the other end, you have these hyper-minimal images like Distroless and Scratch, which are all about security and having the tiniest footprint possible. And what's really wild is the sheer scale of the difference here. I mean, look at this. A Debian image can easily be over 100 megabytes. Then you have Alpine, sitting around 5 megs, and Distroless is practically 0. Now, why does this matter? This directly impacts your container pull times, your storage costs, and the speed of your entire CI/CD pipeline. But hey, it's not just about size. A full distro has hundreds of extra programs that an attacker could potentially exploit. Alpine is tiny, which is great, but it uses a different C library called Musel, which can sometimes cause these really subtle, hard-to-find bugs. Distroless images have no shell at all, super secure, but a real pain to debug if you need to poke around inside. And Scratch? That's a completely empty file system, really only for self-contained static binaries. So, how do we get the best of both worlds, right? Well, the modern solution, the real game changer, is the multi-stage build. The idea is simple. You use a big, convenient image like Debian to compile all your code and gather dependencies. Then, you copy just the final application into a tiny, secure image like Distroless for production. It's brilliant. All right, let's move into the engine room, the run instruction. This is the workhorse of your Dockerfile. It's where you install packages, configure things, but how you write it can have massive, and I mean massive, consequences. So you can write a run command in two ways. There's the shell form, which is simple and what you see most often, but it wraps your command in a shell. Then there's the exec form, which looks like a JSON array. It executes your command directly. Now listen, this is not just a style choice. It fundamentally changes how your container behaves. And this right here is why. The shell form often just swallows operating system signals. So, for example, when Docker wants to stop a container, it sends a signal, a polite request to please shut down gracefully. With the shell form, the shell gets that signal, but your app probably won't. So after a few seconds, Docker just gives up and kills the process, which can lead to data corruption. Using the exec form ensures your app gets that signal directly, so it can shut down cleanly, just like it's supposed to. Okay, here's a classic mistake we see all the time. Remember, each run command creates a new layer in your image. So in this example, you download package lists in layer 1, you install Nginx in layer 2, and then you delete the lists in layer 3. But here's the catch. Those lists are still there, taking up space, bloating that first layer. Your final image is way bigger than it needs to be. So the crucial takeaway is to chain these commands together into a single run instruction using and. This ensures that all the temporary files, like those package lists, are created and deleted within the very same layer. That means they never get committed to the final image. It's such a simple change, but it makes a huge difference in your final image size. Next up, we need to get our application code and other files into the image. Now, Docker gives us two main tools for this: copy and add. And on the surface, they look really similar, but trust me, they are very different beasts.
It's pretty simple, actually. Copy does one thing, and it does it perfectly. It copies local files into your image. Add, on the other hand, has some extra magic features. It can fetch files from a URL, and it can automatically extract tar archives. And this magic, well, it's the source of a whole lot of risk and unpredictability.
Because of that unpredictability, the industry best practice is crystal clear. Just use copy. Always default to copy. It is predictable, it's simple, it's safe. The only time you should even think about using add is if you specifically need its auto extraction feature for a local tar file that you completely trust. So what if you do need a file from the internet? Don't use add. The secure professional pattern is to use run with a tool like curl or wget. This lets you download the file and then, and this is critical, verify its checksum. That's like a unique digital fingerprint to make sure the file hasn't been tampered with. Then you can extract it and clean up the archive, all within a single secure layer.
Okay, so our image has a base, our files are inside. Now let's talk about configuring the environment and the context that our application is actually going to run in.
First up, WORKDIR. You can think of this as a persistent CD command for your Docker file. It sets the working directory for all the instructions that follow. The best practice here is super simple but really important. Always use absolute paths. It makes your Docker file completely unambiguous and just plain easier for the next person to read. Next, let's talk variables. RG is a build time variable. It only exists while the image is being built. It's great for passing in things like version numbers. env, on the other hand, sets a true environment variable that gets baked into the final image and is available to your application when it actually runs. One is for build time, one is for runtime. And this distinction brings us to a massive, critical security warning. It might seem really tempting to pass a secret, like an API key, using an ARG to maybe download a private package during the build. Do not do this. Ever. It is a huge security hole. And here's why. ARG values, even though they're build time only, get burned directly into the image history, which anyone can see with a simple Docker history command. And env variables, they're stored in the image's configuration metadata, also easily viewable with Docker inspect. The only truly secure way to handle secrets during a build is to use modern features like BuildKit's secret mounts. So we come all the way back to where we started. Every single line in your Docker file, from the base image you pick to how you handle a simple variable, is an architectural decision. It tells a story about your application's security, its efficiency, and its reliability. So the real question is, what story does your Docker file tell?